In this lesson, we will design a two-level page coloring scheme to avoid last-level cache set conflicts for a 2 MB working set. We are given 2048 last-level cache sets and 8 colors available. We will solve the plan both mathematically and graphically. First, some key counts. We have 2048 sets. With 8 colors, that means 3 color bits, because 2 to the power of 3 is 8. That evenly partitions the last level cache sets into 8 color groups. 2048 divided by 8 gives 256 sets per color. Now, why 2 levels? Typical page size is 4 kilobytes and line size is 64 bytes. The set index uses 11 bits because 2048 is 2 to the 11. Within a page, the low 6 bits step through 64 cache lines, so 6 of the set index bits vary inside the page. That leaves 5 high set index, bits that are determined by which physical frame we choose. Two-level coloring uses those 5 bits as 3 bits for the coarse color and 2 bits for a fine subcolor within each color. That creates 8 colors, each further split into 4 subcolors. This is powerful because a single page spans 64 sets, which exactly matches a subcolor bucket of 64 sets. Now compute the pages in our working set. 2 MB divided by 4 kilobytes equals 512 pages. First, spread pages evenly across the 8 colors. That is 64 pages per color. Then within each color we have 4 subcolors, so we place 16 pages into each subcolor. Because each page occupies 64 sets, and each subcolor exactly contains 64 sets, this plan ensures we distribute pressure evenly across sets and keep per set contention bounded. Let us draw a conceptual map of the sets. We split the 2048 sets into 8 color bands, and within each band, we split into 4 subcolor slices. Each subcolor contains 64 sets. Next, we build a bucket matrix with 8 columns for colors and 4 rows for subcolors. Our plan is to place 16 pages in each bucket. That equally spreads 512 pages across the 32 buckets. This equals uniform pressure across all 64 sets within each subcolor. Here is a simple allocation rule for page number k, starting from 0. First, compute the color as k modulo 8. Second, compute the subcolor as the integer part of k divided by 8 modulo 4. This round robin over colors. Then over subcolors places exactly 16 pages into each bucket when k runs from 0 to 511. Why does this avoid conflicts? Each subcolor corresponds to exactly 64 sets. A 4 kilobyte page has 64 cache lines, one line mapping into each of those sets. If at most 16 pages in a subcolor are hot at once, then each set sees one line from each of those 16 pages. On a typical last-level cache with at least 16-way associativity, that fits without conflict misses. Even when associativity differs, this even distribution minimizes hotspots and keeps set pressure uniform. Let us visualize the first 10 pages. Page 0 goes to color 0, subcolor 0. Page 1 goes to color 1, subcolor 0. We continue across colors until page 7. Then page 8 wraps color back to 0, but advances subcolor to 1, and so on. Summary. We partition 2048 sets into 8 colors, giving 256 sets per color. We then use a second level of 4 subcolors per color, each with 64 sets, matching the 64 lines in a 4 kilobyte page. A 2 MB working set contains 512 pages. By round robin across 8 colors, and then 4 subcolors, we place 16 pages in each of the 32 buckets. This balances load per set and avoids last-level cache set conflicts.